As we review Chapter 5, there are a few things to pay attention to now that we've talked about all of the derivative and integral rules that we will discuss this year. First, it's easy to confuse the power rule versus the exponential rule. Notice, first of all, the way they look. X to the third. In this example, the variable is the base. That's the variable. The number is the exponent. This is a power, okay? Power looks like this. That's when we use our power rule. So if I am taking the derivative with respect to x of x cubed, I use my power rule. Multiply by the exponent, subtract 1 from the exponent. If I'm doing the integral of x cubed with respect to x, I go backwards. Add 1 to the exponent, divide by the new exponent, and of course plus c. That's my power rule. Exponential functions mean that the variable is in the exponent. This is an exponential function. Again, that means the variable this time is in the exponent. Any variable expression will do. This time the number is the base. The number is the base. So the number is the base, the variable is in the exponent. That's how we know it's exponential. In that case, we use our exponential rules. That looks like this. The derivative with respect to x of 3 to the x is 3 to the x times the natural log of 3. Even if this is e to the x times the natural log of e. Remember, the natural log of e is just 1. That's why the derivative of e to the x is e to the x. Anyway, side note. Integral, if we're doing the integral of 3 to the x with respect to x, that's just the opposite of what we did. 3 to the x divided by the natural log of 3, which is the base. Of course, plus c. So please be careful that you take the time to notice the difference when the variable is in the base, it's a power, versus when the variable is in the exponent, it's exponential. Now what happens when the variable is in the exponent and the variable is in the base? This is neither power nor exponential, therefore we don't treat it like either of these first two cases. In this case, we must make it so that there's not a variable in the exponent because there's already a variable in the base. There's a variable in both places. To differentiate, we must use logarithmic differentiation. How does that look? Well, if we rewrite this, y equals x to the x, then we take the natural log, or any log really, of both sides. It's just the natural log is easier to work with. Then we can use our power rule for this logarithmic expression. So that is now looking like this. Then we do our derivative of both sides. Remember, the derivative of natural log of y is 1 over y, but because it's with respect to x, times dy dx. Remember on this side to use the product rule. So first times the derivative of natural log of x is 1 over x, plus the second natural log of x times 1. And then we multiply by y. So dy dx equals x times 1 over x is 1, plus natural log of x, and it gets multiplied by y. But we usually like to leave our answer in terms of x, so we say 1 plus natural log of x times x to the x, that's y. So, not exponential or power, we must use logarithmic differentiation. Doing integrals, we've never done those, we never will. Not in this course anyway. In exponential functions, the variable's in the exponent, use your exponential rules. In power functions, the variable's in the base, use your power rules. Let's look at another item that gives common mistakes. Integrals of quotients. Now that we've dealt with a lot of quotients, we've seen lots of ways to handle these. Look at all of these quotients. They are very similar to each other. As you know, we do not take the integral of just parts of the quotient. We have to make it not a quotient, or we have to make it into one of our rules. So 4 scenarios here. Here's the first scenario. I ask myself in this first scenario, can I divide or split it up? And in this scenario, yes, I can. So if I'm asking myself if I can divide or split up, that's just another fancier way to say divide, then my integral looks like this. X squared over x plus 4 over x with respect to x, and that makes x plus 4 over x with respect to x, and now I can integrate this part using my power rule, this part using natural logs. X squared over 2 plus 4 natural log of absolute value of x plus c. What if I can't divide or split it up, such as in this second example? I always ask myself first, can I divide or split it up? Because that tends to be one of the easier methods. If I can't, then perhaps I think to myself, U substitution. In this case, for the denominator, I can write that a little bit better for you. For the denominator, therefore, u equals x squared plus 4. I always find the derivative, du equals 2x dx. I solve for dx, I plug back in. So let's rewrite and see what this looks like. X over u, dx is du over 2x. My x's nicely cancel out, and my 2 can go as 1/2 on the outside. Now I'm left with 1/2 integral of 1 over u du, and I know that's my natural log rule as well. 1/2 natural log of absolute value of u, my u being x squared plus 4, plus c. Why do I think of u substitution for the denominator? Because my numerator is looking like it could be the derivative of the denominator. This is of a degree that is 1 less than the denominator. Degree is 1 less than the denominator. Or I say, really what I say to myself, now I say that if it's a power function, but really what I say to myself is it looks like the derivative of the denominator. Not exactly it, because obviously the derivative of x squared plus 4 is 2x, and there's no 2, but it's really close. The constant multiple is obviously easy to take care of. Third scenario, I have x squared plus 4 again in the denominator, but this time x is not the numerator, so I know that I don't see my derivative up here. So this is a scenario where I think to myself, this looks like one of my inverse trig setups, meaning it will integrate to be one of the inverse trig functions. How do I know that? Well, I've memorized the inverse trig setups. So I know that the integral of the quotient, where there's just a constant in the numerator but perfect squares in the denominator, that's looking pretty similar. In fact, I'm thinking to myself that this looks like the arctangent one, which is the integral of du over, we could write it as u squared plus a squared, or a squared plus u squared. In this case, the variable expression is first, but I'm adding, so it doesn't really matter. And then I remember that it's 1 over a times the arctangent of u over a plus c. So in that case, I identify my u and my a. In this case, my u squared is in that position. My a squared is in that position, so I know my u is just x and my a is just 2. So plugging it into that formula, I've got 1 over 2 arctangent of x over 2 plus c. So we look for those two. Look at this last example. I see the denominator, if I took its derivative, is 2x. not plus anything, so that gives me a little bit of trouble trying to think about using that second method. But it kind of looks like also that arctangent setup. However, I'm not supposed to have a variable in the numerator for that. So this is actually a combination of splitting it up and the inverse trig. Oh, I'm sorry, splitting it up, the use substitution and the inverse trig. It's a combination of all of the above. This is a combo of all of them. What do I mean by that? Well, first technique, splitting it up. So let's split it up. X over x squared plus 4 with respect to x plus 1 over x squared plus 4 with respect to x. Well, now we have this one. We solved this with concept 2, u sub for denominator, reference back to problem number 2, and this one we solved with arctangent, reference back to method 3. So put the two together and then we get our final answer. So the answer from problem 2, 1/2 natural log. I'm going to write this giving myself a little bit more space. 1/2 natural log of absolute value of x squared plus 4. The other one, 1/2 arctangent of x over 2, and then our collective plus c. Keep in mind and study these different methods. You'll get used to it, it'll get better. And it's pretty fun. Some important log rules that some people tend to forget. First of all, you have to know that the natural log of 1 is 0, the natural log of e is 1. You just have to know these. Then we have our expanding and condensing rules, like the natural log of a product is the log plus the log, split it up. The natural log of a quotient is the log minus the log. And the natural log of a power, the power becomes, the exponent becomes the coefficient. I reiterate these even though they appear quite simple when you first look at them. For example, for this particular example, you're taking the derivative with respect to x of the natural log of this gigantic expression. And you don't always think that there could be a combination of many of these properties in this one example, meaning I can split this up into 3 different pieces. These are the 3 pieces. I've got a product and a quotient, so let's split it up. The natural log of x plus the natural log of the square root of x squared plus 3 minus, because it's being divided, the natural log of x plus 1 squared. What's the other thing we can do here? Get rid of the exponent. Put the 1/2, get rid of the exponent, put the 2 in the front. So we're using all of the properties in this example. Always expand it as much as you can using our properties. It makes the problem much easier. This is often forgotten when we get carried away in the problem and we're getting excited about taking the derivative. Please remember to expand as much as possible first. Natural log has a lot of different properties. Make sure you remember them. Another one of the common properties that is forgotten is the inverse property. So also remember the inverse property, that the log and the exponential functions are inverses. So the natural log of e to the x is just x, and the e to the natural log of x is also just x. So that can help simplify some problems. Remember those 2 inverse properties. One last thing I want to remind you of is in inverse functions that what that means is that we are switching the x and the y. Carry that into derivatives, and if I'm finding f prime, which is dy dx, then f inverse prime is dx dy. So we have to remember that points get switched, x's and y's, x and y values even get switched, but so does the slope. The derivative gets flipped over, such as in an example where it's just basically looking at, here's a point, f of 3 is 5. Well, what does that mean about on the graph of f? The x, y coordinates are 3, 5. Well, f prime of 3, let me just throw out a value. Let's say I find the derivative and it's 6. Well, another way to look at that is saying dy dx equals 6. Better yet, let's write it this way, dy dx at x equals 3, or I'm going to be even more specific, dy dx at the point 3, 5, because the point is 3, 5, right? So the derivative at the point 3, 5 is 6. Well, if that's the case, then let's talk about the inverse. F inverse at, switch the x and y, so at 5 will be 3. Okay, so that means the point on the graph is 5, 3. If I take the derivative, f inverse, oops, forgot the derivative part, f inverse, I'm going to need more parentheses for this, f inverse prime of 5. Well, remember, we flip over the dy dx to get dx dy. So I take my derivative and flip it over, 1 over 6. What's the way to write that with this notation? Well, for f inverse prime, we are talking about dx dy, right? dy at the point 5, 3. And that equals 1/6. So just keep in mind what we are doing, switching x and y's in inverse functions. That goes for even the dx, the dy for derivatives.